All right. How was spring break? And today I want to talk about operations. So this is the one official MLOps lecture where I'm covering 10 minutes of MLOps probably. Although we're talking about the related concept throughout the semester, and I'm going to show you a lot of related things today too about monitoring and so on. These are the things that you really need when you want to scale to larger systems. And as a running example today, I want to talk about you have a spam filtering feature in a blogging platform, and this is Substack. So a blogging platform that scales so far that you can't run it in one machine. And a spam filter thing, you want to react to different forms of spam, so we want to update this over time. So we want to run this reliably in operations, and we'll get back to this in a second. But what is operations? Operations is essentially the idea of we take a software and put it into production. People are using it, we're running it on a bunch of machines, and we don't want it to crash constantly. Right? So we want to scale it, possibly with more users. If we have so many users that a single server is no longer sufficient to run spam detection, we might need multiple servers for this. Right? We want to avoid downtime, manage operating costs, reduce costs, not maybe buy the most expensive machines if we don't need them. So operations used to be a separate role in a lot of teams. It's a sysadmin role, people who mostly know how to SSH into a Linux machine, set up all the environments, deploy software. The people who used to get woken up at 3 in the morning when some system failed, right? They are on call and they need to figure out how to reset the system. These lines, and we'll talk about this today, are getting blurred more and more. This is the DevOps kind of idea that a lot more developers work on the operations side of things, and a lot of operating jobs, sysadmin jobs in the past, might not have the same priority, or we may have fewer of them. This is usually a very heavy focus on infrastructure, on system infrastructure, installing Kafka on a bunch of machines, rolling out things, testing things automatically, and also hardware potentially. Let's start by what we actually want to achieve. The quality attributes in an operations context are typically called service level agreements. These are the goals, the qualities that you're trying to achieve in operations. Things like having a certain latency. You want to keep latency, like all requests should be answered under 50 milliseconds or something like this. Minimum system throughput. We want to be able to serve 500,000 concurrent users at the same time. Targeted availability. We would like to prefer to be always available, but we usually want to accept some level of downtime because perfect availability is a little bit excessively expensive. So usually you do something like 99.999% available, which is something like half an hour of downtime a year, or sometimes lower levels like this. Time to deploy and upgrade. So if you want a new version of the spam filter, how long does it take until all the users see that feature in production, right? From me committing this. Durability of storage. Are we losing data all the time? And you can have all these properties, and you see this is not directly of the software. This is how the software is running in production on a server in a network. And you can do this for the system as a whole or for individual services like the spam filter service. What are some, in this specific scenario here, you're running a spam filter on a very, very popular blogging platform. What are some reasonable service level agreements that you might expect? What are some of these goals you might have?
Being able to process like a certain amount of articles a day.
Right. So articles or comments, right? So you have a certain throughput requirement that's usually very bursty. So you don't necessarily have very even rates. So you probably don't care about throughput necessarily across the entire day, but peak throughput or something like this, you may have some goal of processing, I don't know, 100,000 comments in 10 minutes or something like this in peak hours? What other requirements might you have? Including the ones we just talked about, what are some reasonable expectations?
I guess error rate of the spam detection system being below a certain benchmark, like maybe like less than 2% or something.
Right, so if you're thinking about how many requests fail in the system, right, maybe at most 2% of them fail. I think often we have this more as availability of the service, right? So that includes like hardware availability, network connections. What would you think is reasonable expectation for a system like this? What level of uptime or downtime? If you're familiar with operations language, how many nines? 99.9999999, how many? So let's say 99% availability. How much downtime do you allow in a year? Yeah, close to 3.5 days roughly. That sounds like a lot. Maybe not quite. I mean, maybe the spam filter isn't important enough that might be okay. Or maybe you have slightly higher standards. 99.9% is how much downtime? 10 hours, 8 hours, something like that, right? That sounds okay, right? There's some downtime that you might expect. You could go down 99.99 to an hour, essentially, right? And then 5 minutes or something like this. The point here is typically the more availability you try to guarantee. And if you're Amazon or if you buy hosting services from somebody, you can write this into a contract, and there might be penalties if you have outages more than that. I think Amazon had several outages last year, pretty large ones, well-known ones that usually lasted for several hours, right? So I don't think they got more than 2 nines on their AWS instances. And if you look at a single instance itself, they crash all the time, right? So you need some sort of redundancy to have higher outages. But even the system-wide outages for AWS were pretty high. So you can usually buy more redundant services. Maybe you buy servers at Amazon, at Microsoft at the same time, or you have some local ones in addition. It just becomes more expensive, right? With all of these things, higher reliability is more expensive. And at some point, it might not be worth it for a spam filtering feature, right? It's similar to the risk analysis. How much do we invest in mitigation? What's the risk of failing? There's a where is this? No. Where do I have the error budget thing? So there's a nice philosophy, I think that came out of Google as well, about having an error budget, saying you have this amount of outage in a year that you're allowing. And if you're going far below that, if you're much more reliable than that error budget, you're probably investing too much into redundancy and this. You can probably run this at lower cost. Right? So the goal here is not necessarily to aim for perfection, but to aim for something reliable that you can negotiate, right? That's reasonable in the terms of cost of providing that functionality. So you can negotiate agreements and budget, but you can often get lower availability for a lower price. And depending on your system, that might be well worth it. So in an end, this is a risk management role. You're thinking about how frequent outages or what latency or what scalability can I support, not complete risk avoidance. And with machine learning, this becomes, it's actually not that different, and that's what I'm trying to convince you throughout the lecture today, that MLOps is not that different from DevOps in a lot of ways. it's a very similar role. How much should our models be available? How many concurrent requests do we need to serve? What latency are we trying to guarantee, right? How many updates do we run? How easy should it be to update the system? So it's very similar things of just deploying models, and we have different hardware requirements. We have different, like large models might be different from smaller containers, but the concepts in itself are kind of very similar. And you see kind of consistent themes throughout. Observability, monitoring is really important. I'm going to talk about this today quite a bit, and then I think next week's lab is about monitoring, and then in milestone 3, we really make you all do monitoring of your systems. There's a lot of release management. Infrastructure as code, you have already seen containers, but there's much more in this space that you can automate a lot of infrastructure things, and then really scaling, and nobody wants to do incident response planning, but we might talk about this briefly. So DevOps came out of this. I don't know how much people actually remember this these days, but developers and operators didn't usually have the best relationship in the past. It's kind of this, oh, it worked on my machine. What's the problem in production? The answer of the operator to that is then, yeah, then let's put your machine into production. There's a lot of conflicts. Do you know some of these conflicts traditionally? What makes operations or the relationship between developers and operators so difficult? What are some of the release problems that are common? Yep.
Like network compatibility. Like sometimes the system can work fine in IPv4, but like doesn't work in IPv6.
Right. So you have certain assumptions in your development environment, for example, what network libraries or what network connections you have, and then they are different in production, right? And nobody communicated that.
Dependencies management and library versions.
Right. So you expect GCC version something on your machine, that's what you compiled everything, and when they try to run it with an older version of that in production, it just doesn't compile, or some dependency is missing. We got better at this. If you're these days using PyPI or NPM, you typically declare dependencies. There's still a lot of problems if you have an older version, but you're floating things and something newer installs on a system, right? But we get much better at this, and containers solved a lot of those dependency problems. Any other issues that you may have experienced or heard about? I think I have a whole list here. Yeah, missing dependencies, I think, is the most common one. Different compiler versions, different local utils. Like, for some reason, the Mac version of grep is different than the Unix version of grep. So if you rely on that in scripts, it's weird. Database problems, do you really have the exact same schema? If you make some local changes, how do you get them into production? Operating system differences, do you have the same version of Linux, or do you develop on Windows and then deploy it on Linux, right? Something is just too slow to run in production. It works fine in small tests on your machine, but if you actually have hundreds of thousands of concurrent users, right? So those are all common problems. And traditionally, you have this disconnect between developers and operators. Developers try to finish their code and get some functionality running, whereas operators really focus on cost and risk. Like, how can we scale this? Can you really not make this algorithm faster? Do I need to buy a much bigger machine, right? If we want more users, this is really expensive. They focus on monitoring crashes, monitoring load spikes, and so on, and rolling back releases. So we see with DevOps these things coming closer together. Quality assurance is kind of a connecting thing. So if you test your software locally, that doesn't mean it's already ready to be put in production. We talked about testing in production too. That really needs buy-in from operators. You put the system into production, you need some monitoring infrastructure to see how it's doing, whether your predictions are any good, whether the system is running. If you want to do A/B testing, you need some infrastructure support for that, right? And you need to be able to update things quickly, to roll back things quickly, and so on.
Is it not also a kind of bottleneck in that, like, the ops people don't have the context of the feature? So
right.
Why was there like a fork in the first place? Doesn't it waste time in case? Isn't it always helpful for the ops people to know or be involved in the development?
So that's often a discussion, like, do the ops people need to know more about the development or be integrated in this, right? So if you notice a problem in production, do you have the knowledge to fix the software, or do you need to go back to the developers and ask them to change something? And traditionally, they didn't have the involvement with the software, right? They would install patches, and if the patch doesn't work, hopefully we can roll back, right? And then tell the developers to change things. Traditional update cycles were really long. So when in the 90s or so, if you wanted to buy a new version of Windows, a new version would come out every 4 years. I mean, often took a little bit longer. They were often late. So if you were working at Microsoft as a developer and wanted to get a new feature into Windows, you have this window, 3-year window, and then there's like half a year before where they close everything, now get ready for the release. And if you don't make that deadline, well, your feature isn't going to get shipped for 4 more years. So you won't know for several years of whether anybody in production likes your code. Whereas these days, in a lot of companies, we release things pretty much to production as soon as you commit them to GitHub and maybe a few tests pass. Etsy was one of the first companies pushing this really. Code was in production within half an hour. You wrote something, you pushed it, you could see it on the website live in production in half an hour. As a developer, that's super empowering because you can see immediately whether somebody likes your code, you can tweak it, you can learn from how users are using it. This doesn't work if you have 4-year release cycles, right? And DevOps is really the idea, can we automate this? Can we make this, put these things closer together and update more frequently? So I've been talking about this already quite a bit. DevOps is just the idea of bringing developers and operators closer together and having joint responsibilities. This is a typical graphic for showing this, that DevOps is like this continuous process that involves both developers and operators, and the lines kind of blur over time. So developers create code, plan code, create it, verify it. So this is the testing part, maybe package it, put it into a container, release it into some platform, and configuring is kind of setting up the hardware and monitoring it, and that goes immediately back into planning. The idea here is exactly this. You type code, you see it live in production maybe in half an hour. You can immediately monitor whether users like it, so you can immediately continue planning, right? So you can go through the cycle much faster by getting faster feedback. So DevOps is kind of hard to pin down. Depends. MLOps is even worse. It means everything to everybody. It's a marketing term to a large degree. But the idea here is pretty much better coordination between developers and operations. We really want them to collaborate, or increasingly they get unified in a single role. Like AWS talks about how they don't really have separate operators. They have developers that also do the operations things. And the key goal here is really to reduce friction of bringing updates into production, right? So we don't want 4-year update cycles. We don't want it to take a week either to install an update. We want code to get into production quickly. We want to be able to update quickly and learn from it. And to do this, you kind of need a consistent tool chain, automation, lots of documentation and versioning typically so that you can roll big things. This is called configuration as code. And this is really heavily focused on automation, on doing many small incremental updates rather than few big ones. So this is often defined by tools. There's a lot of tools in this space and lots of automation. And you've seen some of those tools. I mean, in this diagram, you probably have seen tools for most of these areas. This is a couple of years old, but it hasn't fundamentally changed. I can walk through some of these ideas. It's hard to draw the line what's still really part of DevOps versus what's kind of more broadly, but you start by a ticket system, Jira or Trello, or some sort of list of things you're doing. You have some communication, Slack maybe, and some knowledge sharing, some wikis or so. But then really version control is where the coding starts. Everything is in version control. So you can always point to a specific version. You have continuous integration. We talked about this. Every time you make a change to your software, it automatically runs tests. You have build automation. So during CI, your code is probably compiled, probably deployed. This is GitHub Actions to a large degree these days, and lots of other build systems. Testing, we have a lot of automation, all kinds of test automation. You're probably using PyTest or something like this in the current milestone. And then deployment, there's lots of things of how do we deploy things in production. Simplest thing is we SSH into a machine to copy files, but there's also all kinds of more complicated things, automated things, and often we use Docker in the process or containers or things like this to ship larger units. I'm going to talk about this a little bit. If you have more than one machine, it gets really annoying to set up every machine with the same dependencies. So there's configuration management tools. And then you can manage all of this at in the cloud at massive scale. So you don't buy hardware. You just rent it from AWS and have potentially things where you need to scale hundreds of containers across thousands of machines. This is the Kubernetes of the world, kind of this infrastructure to really scale that. So the themes that we're seeing is infrastructure as code is, I come back to this in a minute, but can we do setup of machines, dependency management through scripting rather than SSHing into a machine doing a lot of interactive things? Continuous integration, running tests automatically, containerization, orchestration, like managing things across many machines, and then software deployment and measurement. Maybe just to briefly describe buzzwords. Traditionally, releasing software into production takes a while. Traditionally, this is, we're going to take everything offline at Sunday, 1 a.m. So the ops team needs to get up at Sunday, 1 a.m. to do this, and then hopefully the system is back in the morning. And if they struggle, then it might be unavailable for a little bit longer. This was a slow and kind of inefficient process, and you can only do this once a month or once a week or something like this, and the team doesn't like it. And so traditionally, you have maybe a engineer commits something, it gets built, and then somebody needs to approve it, and then some tests run, and somebody needs to approve the next step. So there's a lot of delays in these pipelines too. So the first step was always just, let's automate all of this, let's get the humans out of the loop, and that's what's known as continuous delivery or continuous deployment. Similar to continuous integration, where once we commit something, we run all the tests. This is now once we commit something and the tests pass, we also automatically deploy things into production. Right, so what we have here is we run the tests, we stage it, put it into a container, move the container into production, see whether it works in production, and maybe roll it back. And there's one distinction here between continuous delivery and continuous deployment is whether there's a human still in the loop somewhere to just say it's okay. Right? Continuous delivery essentially just says everything is automated, but some human still needs to press a button. And continuous deployment, that's the Etsy model. You push something to your code base, and it shows up completely automated on the website half an hour later, right? Whatever you commit. And again, this is super empowering to developers. A lot of developers really like working in those spaces where they see the effects of their code very quickly, right? Where you can experiment, where you can get feedback from your users, whether you see that they like things. Let's talk a little bit about the tooling involved. So we've talked about containers before. This has helped a lot and is probably one of the key innovations in a lot of DevOps culture, is that rather than here's some code and some instructions of how to compile it, we now put all the things into a container, and the container essentially contains all the dependencies, right? So if you need to figure out what are all the Python dependencies to install and which version of your libraries to install, you do this when you create a container, and it's typically the developer's responsibility now, right? It's not that you give your source code to somebody who just does containers or to an operator who puts it into a container. We give the developers more responsibilities. These days, you're pretty much expected that you know how to put something into a container. And then for the operator, it's much, much easier to deploy something. It's just a container name. And there's typically some infrastructure of how to upload and download containers. And they don't really have to worry about a lot of traditional dependency issues. They only need to worry about, do they have enough machines where they can run all of those containers? Do they have enough resources to run them? And in your project, you're also going to put all your stuff into containers, right? So you can use more than one machine. You'll probably be fine with just using the virtual VM that we provide, but you also have these $50 in Google Cloud credits, and you can find other machines somewhere. So if you want, you can create another virtual machine, put some data there, put some containers there, right? Create a distributed network. Right. You've seen Docker before. So let me jump forward to monitoring. So monitoring is honestly probably the most useful thing that you can learn in this class. It's something that I completely underappreciated until a while ago. And these days, whenever I write something that runs for more than 5 minutes, I put monitoring in first. Monitoring gives you a lot of power to observe how a system is running. And it also saves you from having to look at it the entire time because you can get alerts if something goes wrong. And I want to, has somebody here used Prometheus Grafana in some project before? What have you used it for?
So I got kind of like a server that can scrape the jobs for me, and I have a dashboard to see the pipelines.
Okay. So like a long-running jobs. What are you monitoring? What are you looking for?
Like, so I got several official jobs websites, and I got crawlers crawling them every 24 hours as cron jobs, and they went into pipelines to parse them and find the best fit for me.
Mm-hmm.
And so there will be a funnel processing those jobs, and I got a dashboard watching out the funnel.
So you want to see how many postings there are, how many are surviving each step, kind of seeing how the thing is running? Okay. Somebody else over there was also saying?
Yeah, so we use it for the caching systems, Redis, to observe the cluster. So basically, what's going on in the cluster, how many reads and writes. So Redis exporter uses the Prometheus format.
Okay.
Values in terms of time series.
So you had Redis and monitoring system to see how Redis was running, or cluster of them. What were you looking for?
Mostly the peak timings where most of the reads are happening.
Why did you care? Why did you want to know that?
So basically, back when I was working as a SWE, we used to run batches of accounts, their portfolios to calculate bars and leaks, beta, etc. So we just wanted to know the peak timing when the cache is being invoked for certain data sort.
Sorry, why did you want to know this? Was this for provisioning hardware? Yeah. Kind of seeing how many requests are you actually getting, and am I running out of time?
So we had built OCR pipelines to ingest documents and then extract it. So when a user raises an insurance claim, it's usually in a document. So to process that entire thing, to ingest the document, see what kind of claims are they raising, what is covered, what is not. So we had an entire pipeline for that. And in that, we used to monitor how much time it is taking for each document to get uploaded, for OCR to get completed, and all those things. What is the peak? What's the peak load? So sometimes the uploads used to happen in batches. Yeah. So then we can provision our hardware according to that. We can see what's going wrong, what are the error rates.
Okay. So again, seeing how much demand do you have, how much do you need to scale the system, is something failing, right? So I can show you a little bit of. This is from the simulator that I'm running, and no. this is some data. This is over a week. And you can see something weird is going on there. Right, so this is average ratings of each team. And then this was completely spiky for some reason. And looks like you were all doing weird things. And it was during spring break, so I don't expect you were all doing weird things with your predictions. Right, so I started looking into this, and I actually caught this very late because I disabled all the alerts at the end of last semester because I don't want it to alert in the break. And then I forgot to update this again. What was happening, so there's a bunch of things that I'm monitoring here. This was memory of the simulator that's running on 2 machines. And we were getting closer and closer and closer to the max memory thing. And then my system was just running out of memory. And at that point, it's queuing requests to ask notifications from you, and it can't process them fast in time. It's just running garbage collection the entire time. So it was just creating outages and so on. So once I realized this with like a 2-day delay or so, I added another machine and kind of gave it a little bit more memory. There's a couple more like this. I have a monitoring thing here about disk space. I'm running very close to maximum disk space on the main disk, and I kind of need to watch that carefully. Like this is where all the Kafka data from your teams are stored, close to 2 terabytes there. So this is the kind of stuff that I'm monitoring to see whether something is going wrong, whether I have enough machines. There's lots of other things where I can see that something was going wrong. This is the Kafka traffic internally that I was monitoring, and this is where all the memory problems happened, right? I could have monitored any of them for abnormalities. Like when there's suddenly almost no Kafka traffic, it should notify me. So this is the kind of thing that you can do with monitoring. You can also do much more domain-specific things, like I've shown you this plot a couple of times, right? So this is the average ratings of each team to see how your models are doing, essentially. You're doing some online evaluation right now, and for the next milestone, we want you to monitor this. Right? So it's some form of trying to figure out some ground truths, seeing how different models compare. You can do this. This is the API requests, where you look up movie names and user names, user data, how many requests I'm getting per hour. Apparently, some people do live requests, so this tracks pretty much the requests that I'm doing. I have no idea what you're actually running there. You can also see the anomalies where this dipped down to a very low number while the outage was essentially happening. The way to implement monitoring is confusing at first and then super easy afterwards. And I want to show you a couple of things of how this works. Let me start by showing you some code, I think. So you don't really write monitoring code from scratch these days. You use some sort of library. Prometheus is one of the most common ones. There's several other ones. And the way that this works is that you, with this library, create a counter object. So this is just something that you can later observe in a dashboard. This is for monitoring submissions to Canvas. This is a slightly different project, but it's counting how many submissions have I processed in total. It's just a counter. So the more, every time I'm processing a submission, I can show you that too. That's not exactly the same thing, but this is running in a loop here, checking. I'm running checks now, so I'm increasing the counter. Then I'm checking for new submissions. It's happening somewhere here. I have a processing queue. I'm putting a value into how far am I behind. And then I'm increasing a counter if I see any errors. And I'm observing how long it took me to process one of these iterations. So in the code, this looks really simple. It's just increasing a counter. The way that Prometheus works with this is Prometheus runs a web server in your application to essentially report these results. This is not the one I wanted to show. This is the one. So this is for the data that I've just shown you. So I can collect metrics on some port, which you configure once you set up the library. And it will just return in a text format a bunch of metrics. So for example, it says total cycles checked is 29. In my case, this just increases every 10 minutes by 1. It says what's the current queue size? It's 0. It has something. This is a little bit more complicated. If I want to show a distribution, it would be very expensive to store every single observation, how long every single one of these took, if there are many. So it stores a histogram. So what you're seeing is here, I had 29 requests. How many of them took under 0.01 seconds? None. How many of them took under 10 seconds? Most of them. How many took longer than 10 seconds? A very few of them. Right, so it's aggregating this. I can show you another one of these. This is web requests to the server with the movie metadata. So it shows here I have gotten 5 million requests since I started the server. If I'm updating this, if I'm just running an update, you see these numbers going up every single time. Right, so Prometheus, what it's doing in your application or the client library is very simple. It's just producing this data. So in your code, you're just increasing a counter, and it produces this update. And then you have Prometheus, the actual code, that's a database observability platform that will pull this data every 5 seconds or something like this. So it will send a request like this every 5 seconds and collect this data and put it into a time series database. So the way that this looks in Prometheus then is something like this. I can look at how many, Prometheus, what do you think, how many requests per second did I get? So you see the 5 million here. I can also go back in time and look at past values. So it will show me this value at different points in time. And I can also plot this value. So this is this value over the last 2 days. So you just see that this value of how many requests were processed just increased over the last 2 days. So far, so good? So a relatively simple thing. I have a counter in my program, and I have a separate thing that's just collecting this data and storing it in a time series database. And now the fun part is that you can do queries over this. And I'm not going to show you the entire query language, but I don't really care about the absolute value here. What I care about is, for example, how many requests do I get per second or per hour. And there's a query language for this. This looks something like this, which just tells me, give me the increase of this value in the last hour at each point in time. Right? So I can plot this here. This is how many requests I get in the last hour prior to this point in time here. Does it make sense? So it gives me this query language, and I can do fairly flexible things if I care about the request per second. No? Oh, wait. If I care about requests per second, this is, I think, what this is doing. Rate instead of increase. It's not the absolute increase. It's the rate, the increase per second, on average over the last hour at every point. If I make these intervals here smaller, this gets much more jiggery, right? If I want to have the average sliding window average over a day, this is much more smooth. And you can also do computations, like I had this. So this is a sum of how long this took. So I can see what was the increase in time. Oh, come on. Divided by the increase in requests. So this tells me the average time that one request took, essentially, right? So how long did I spend in total answering requests? By how many requests have I answered? The point is not this specific query. The point is that you can run queries like this. And then Grafana on top of that is just a nice dashboard that takes this query language. You can write queries like this, put this into a nice visual dashboard, and create alerts. Right? So I've shown you this one here before. Oops. If you look at what this is actually doing, it's one of these queries that I just shown you. It's the increase in this rate. I can show you. So this is the average rating. For average rating, it's just another query. It's a sum of the ratings divided by the count of the ratings, aggregated by team. Again, the specifics don't really matter here. It's more that you can do this. And once you know how to think about these query languages, it's really straightforward to do. It's very easy to introduce another monitor in your system, or another counter. All that you're doing is really just you define a counter or you define a histogram, one of these values. There's only 4 or 5 of them that you care about. Counters is the easy one, is the most easy one. You set up Prometheus once to monitor this. Like I can show this here also. It's monitoring a bunch of different systems. It's just pulling from a bunch of different systems data. And then you use Grafana to create a nice visual dashboard of this, which is pretty and has alerts. So if some of these metrics go below a certain value, it's supposed to send me an email. Right? I can inform you in Slack and so on. My point is not so much the specific system here. You see this in the lab next week of how to collect this data, how to create queries, and so on. The point is, this is really useful technology, and it's very easy to use once you know how to use it. And if you ever want to run a system that runs for a while, this is probably one of the first things you want to do. See the health of your system, see how fast you're responding, see how many requests you're dropping, and so on. It's very easy to set up, and it gives you a lot of information. It can wake you up at 3 in the morning if you set it up to actually ping you. But it also prevents that, like me, you're not realizing for 2 or 3 days that the system wasn't actually working, right? So, and it also allows you to run these experiments in production, to compare different results, see which model is doing better, all these kind of things. Make sense? There's also a bunch of pre-configured collectors, like system performance metrics, like how much disk space you have and so on, is a predefined tool that you can just install called Node Collector. It just exports a lot of system statistics, and you can have predefined dashboards to see things like available disk space and so on. You don't have to program every single one of these yourself. How many of you have worked with software that ran on more than one machine? Some of you who worked in production, yes? What were you working on?
It was for DOT's contractor for nuclear data submarines communication system.
So did you need many machines to scale it, or?
As per the submarine requirements, they required multiple server racks and communication.
Okay. So I assume most of you have not done this. Most of the software that you developed ran on a single machine. Is this true? So you don't know the pain involved of setting up software across many different machines. The first step that's usually annoying is when you get a new machine, somebody installs the operating system. Hopefully it's not you. And then you SSH into the machine and set something up. In the simplest case, you set up only Docker or Kubernetes client or something like this, but you set up something. Talking a little bit more about kind of inside stuff here. So my simulator is running on, is currently running 7 different containers or so on 4 different machines. I added one machine to it because of the memory issues. So The simulation itself is now spread across 3 machines instead of 2 before. So for that machine, I got a virtual machine for that. I can log into that. Now I needed to go in and install Docker. After this, I needed to install the node collector. So this is a metrics thing that collects system statistics, like how much memory. I had documentation for how to do this. And I do this rarely enough that I always have to look this up. So let me find this. So this is a blog post that I follow for how to install Node Exporter. Pretty annoying, multiple steps. First, download it, fine. Unpack it, fine. Go into that directory, copy the file somewhere, remove the rest of the stuff that I no longer need, change the permissions on that file, create another file that sets this up as a service. I didn't need to create a user for this, but then set this up that it runs automatically with the machine, that the machine restarts. It's not hard, but it's like 10 steps or something like this. Then pretty dumbly just copy-paste into the terminal. And now if you have more than 3 machines, this becomes really annoying. Right? I don't want to SSH into 100 machine each time set this up. And this is just infrastructure. Everything else is running in Docker later. And there's like, it's not Kubernetes, it's Docker Swarm. It's some layer over top that decides what to run where. But I need to set up the basics, right? And occasionally I may need to install security updates. And I need to do this on all 4 machines. And again, 4 machines is small in this context. If you have 100 machine or more than that, this becomes really annoying. This is what software configuration management software is for. So this is the kind of software that does provisioning, that runs scripts on many different machines. Ansible and Puppet are probably the biggest ones in this space. Chef is another one. What this does is it has essentially a script of what to run on those machines. And I can show you what this might look like for the node exporter thing. Come on. It's not short, and this is LLM generated, so I'm not actually using this. But this is pretty much what the blog post was saying. First thing is download the file. Second thing is extract the file. Third thing is copy the file to a new location with permissions. It's a domain-specific language. It has certain abstractions for common things. What this does in addition, it runs this and checks that it actually succeeds. So there's some additional management infrastructure. And in the end, I just would run Ansible, run this on this list of machines that are typically configured in a file. And it SSHs into these machines, hundreds of machines in parallel, runs these scripts, makes sure that they all have the same, execute the same steps. Right? Puppet is another one that, oh, this is very poor contrast. It looks a little bit different, but the idea with Puppet is that you're not necessarily describing what are the exact steps, but you describe what's the end result of what the system state should look like, and Puppet will figure out how to get there. So you essentially say, I expect this file to exist, and Puppet will check whether it exists, and if not, will create it in a way. Again, the specifics don't matter. This is the kind of stuff that you can look up when you need it. But this is a kind of DevOps infrastructure that's really useful out there to execute the same stuff across many different files. And then the benefit is you have this script here that I can put into version control. Right? It describes how to set up my machines. And if I need to install a new version of the node exporter, I can update this in the script, push the script into version control, and run that thing over all machines. I don't have to go back to the blog post and remember what I did last time. Right? I can update this in a central place, and I have documentation what I ran on each machine. Does this make sense? This is really useful infrastructure if you're running things across many different machines. And then the final step in this evolution is probably Kubernetes or related systems, but that's probably the most dominant one right now. This is taking care of where to run your containers, and has millions of other features. So it can think about, you have maybe 50 machines, some of them with a GPU, and you have 20 containers. And now the question is, which container runs on which machine? Which container needs multiple copies that run on multiple machines? How do you route requests between them, like the network traffic, load balancers, and so on? If I want to update one of these containers, and it may run on different machines, I run one Kubernetes command, and it figures out where to do it, and it does rolling updates, so it doesn't change all the copies at once. So that's the kind of functionality that it does. The way that this looks is, it's a typical distributed system. You have all your worker machines that essentially just have I think it has Kubernetes host infrastructure, and then it runs pods that are containers in some way, and the central server decides which container to run where. It can also manage to get more virtual machines from AWS, configure them, and put your containers there. AWS is also happy to do that for you, right? So they have lots of similar infrastructure where you essentially just say, here's a container. If you get too many requests, we're happy to make more copies for you automatically on demand. We just give us a credit card and you'll be fine, right? This is the kind of infrastructure that's really helpful. We're going to show you Kubernetes in a lab in a couple of weeks. I would not strongly recommend to use it in your group project unless you have some interest, right? Kubernetes is one of the most complex systems out there, has a steep learning curve. It's very powerful if you need that kind of thing, like to run a big distributed system, but maybe not the kind of thing that you want to voluntarily do. Yep.
How common in practice is people using Kubernetes versus just doing a container in AWS?
I think a lot of organizations use Kubernetes. If you have an in-house team that manages this, you do this. You can also buy into AWS or another system to let them manage everything for you. That's often a little bit more expensive, and you buy in specific infrastructure, but it has less overhead on your side. All right. With this, I'm finally getting to MLOps. I told you in the beginning already, this is not really different from DevOps. It's just slightly different tools. Right? So you see different diagrams. I don't know that it really matters. The point, again, is to bring updates quickly into production. So you want to be able to experiment with models in production, run updates in production quickly, and you don't want to have this thing where you SSH into machines to copy pickle files manually and something can go wrong. Right? So it's integrate machine learning artifacts, models, training jobs, and so on into the software release process. Unify everything, automate everything, automate some testing in the process. If you're training, do some data validation. Do continuous deployment of models where you can essentially run a training job and it automatically deploys the model into production. It packages the model on a serving infrastructure, puts it into a container, puts the container with Kubernetes into the cloud on a machine with GPUs. It has versioning that we often don't particularly do well with models. So you start versioning this and you discuss it in, you monitor it too. There's a tooling landscape. This graph is from 2020. There's an updated version. It's nowhere near that I can fit this on a slide or show anything meaningful here. It's everybody who wants to sell a tool in this space calls it MLOps. It's a big marketing term these days. There's so many tools out there doing all kinds of different things. But the key principles are automation, testing, observability. And these are the most common classes of tools. Model registries are places where you upload models. If you have many models in an organization, you have some metadata, you can download models from. Think of this similar to NPM for models or PyPI for models, right? A place where you can upload models, download models, document them. Model monitoring is a monitoring system, not that different what you could write yourself with a few lines of Prometheus instructions. It typically monitors the predictions that you made. It logs the predictions. If you have some way of getting ground truths, we talked about this in the testing of production lecture, it can try to do accuracy metrics for you, can show this kind of stuff. Right? A lot of pipeline automation and workflows. How do you run long-running training jobs? How do you run jobs that have many data processing steps that might be in some pipeline? So you can play with some of these if you like Airflow. DVC does model versioning in the process. We're going to show you this a little bit later. Model packaging, we have mentioned briefly in the deployment lecture. This is essentially taking a pickle file and turning this into a high-performance inference service that might run on a GPU. Right, so rather than you writing a Flask script to serve that model, it does this with a few lines of configuration and often focus on high performance stuff. Distributed learning, distributed deployment. There's like lots of frameworks in this space. Feature store, we briefly mentioned, is like pre-computed features, documented features in an organization. And then you have large platforms that essentially do all of this in the walled garden. AWS SageMaker is probably the best well-known one of those. If you stay in AWS SageMaker, you do all your modeling and versioning and inference there. It's nice. They do versioning for you. They do monitoring for you essentially for free because it's all in this walled garden. They can observe everything. Right. Any questions? I honestly don't think it's super interesting to go through those tools one by one. You've seen some of them. You've seen Weights and Biases, which is a platform that can serve as model registry, does some versioning if you want, integrates with testing. MLflow is a very similar open source version of that. I'm going to show you DVC later. But I think that more traditional DevOps tools are often more useful as a foundation, especially monitoring, especially containers, updating in that way. The mindset is pretty much the same as for DevOps. Think about the entire process, think about the tool chain, think about automation. Try to automate everything, that you can go from a button click into production. In Milestone 3, we actually ask you to do this, that you can do updates of your models and deploy them into production pretty much fully automated. And we're going to ask you to run A/B experiments in production. So you need some monitoring infrastructure. You need some ability to update models, to run multiple models at the same time. Right? Elastic infrastructure means you can scale with demand. You can add more servers. You can have more copies of each machine. Right? You can document, test, and version everything. If something is in a container, it automatically documents all your dependencies. Right? You can version that container file. And you want to iterate and release frequently. All right, I did enough talking. I want you to do some talking. So think back to this spam filter example for Substack or some other big blogging platform, and imagine you want to run this in production, right? Your Substack is running, you want this fairly reliable, and you want to update this occasionally. I want you to answer two questions. Which DevOps or ML goals to prioritize? So what are you trying to achieve? Rapid updates, experimentation, and so on. You can go back to the slides what options might be. And which tools to explore or invest in first? Right? I'm not expecting that you know all those tools, but based on the things that we talked about, these lists of things, what do you think is an important problem where you would like to look into a tool and try to automate that? Clear? Go for it. All right. Shall we talk about it? I don't think there's any single correct answer to this. So I just want you to kind of explore what do you think is going to be useful here? Where would you spend most of your time? And if you need different candy, Claire brought her own.
Sometimes you're in the mood for trashy candy.
It's fine.
We're not all snobs all
That's-
the time. I'll bring the Skittles next time. I didn't have enough room in my bag. But I got some delicious Kit Kats. But if you want some of his bougie dark chocolate, I can also deliver that if that's the cost of...
There's some volunteers up there and
See,
there.
Kit Kats, Christian. Eating on my terrible American candy.
First of all, I think what we can think about is pipeline automation and also storage, memory, optimization, and also for high availability. Like, so one server is down, like we should, like the other server should go on. And
So for pipeline automation, you're thinking training mostly?
trains.
Pipeline automation. Yeah, for updating our models once
Right.
we've monitored. Yeah.
So you get new data, you train regularly or something like this, and you want to automate that essentially.
Yes.
For example, yeah, this is pretty much what you're going to do, I think, in Milestone 3, like a nightly build or so with most recent data, right? Train, like curate the new data, update the model, put it into production. Yeah. And the other part was scalability, right? What would you explore for scalability?
Actually, I told like reliability. Actually, so
Okay.
like for maybe you use like some metrics like benchmark for calculate for reliability, like some points. Like if it holds like some X point of threshold, so we can use trigger for that.
So monitoring more,
Yeah,
right?
monitoring.
Okay.
Yeah.
So monitoring, maybe even taking automated actions based on that, like rolling back a model. Yeah. Right?
You're pointing at someone.
You're the volunteer back there. There's a hand.
Am I crazy? Oh, there.
One of the goals could be continuous integration and deployment. We could incorporate some GitHub actions to ensure that.
What would you test in continuous integration?
The build, we could have some tests for the model, like unit tests, smoke test kind of stuff.
Run some sort of accuracy tests, maybe behavioral tests, also some critical tests, and then, before you put that into production, automate that every night. Yep. Right? Anybody has a different direction you were going? Just want to shout. Monitoring? Yep. Yep.
Like, especially for favorite, if you don't know a certain account, the cost would be the escalation would be to like block that user. So I feel monitoring the previous step to escalations. So
yeah. So monitoring, especially for certain behaviors, is going into analysis, right? Finding systematic problems. You can do this with monitoring infrastructure. You can do this with other data infrastructure. Kit Kat or chocolate? All right.
I found that very validating. Thank you.
All right. I have two more points that I'm going to go through very quickly. First, this is something that I'm going to tell you about that none of you are going to do, I'm pretty sure, but I'm going to tell you about it anyway. Incident response planning is have a plan what you're going to do if something goes wrong. So essentially plan for mistakes before they happen. The issue here is, let's say the spam filter goes down at night and suddenly people post a lot of really toxic stuff on your website. What do you do, right? Let's say this blows up on social media. What do you do? This gets into the New York Times front page. What do you do, right? Who do you wake up? Can you shut down the system? Can you fix it? Who speaks to the media, right? Those kind of questions. You don't want to deal with those kind of questions and figure this out on the fly at 3 in the morning when your phone blows up, right? And people complain. Ideally, you have a plan in advance. Maybe you've done some hazard analysis and have some idea of what the things are that could go wrong. Maybe there's some common things like outages, attacks, or so on that you can prepare. You can also think the ML component is fundamentally unreliable. What if our model makes completely racial biased things and people start complaining about this? Right? So a lot of this is thinking about who to talk to, have an expert on call, maybe design a problem for anticipated problems, be prepared to roll back something, have a baseline in mind that you can switch over to, prepare for recovery, maybe have a backup, those kind of things. And this is all stuff you can do in advance while you're not panicking at 3 in the morning. And again, I think most of you won't do this in advance unless it's a big company that has some kind of policy to do this. But I wanted to talk about this. The other thing that I wanted to talk about briefly is organizational culture. DevOps and MLOps is interesting in that it is a culture change for a lot of organizations. Like, how do you get people to get away from these big divides between developers and operators? Not everybody is comfortable putting code immediately into production when you commit it. Not everybody wants to do all the operation stuff that you had specialized people for in the past, right? Now needs to deal with hardware, and now I need to deal with containers, I need to learn monitoring, things like this. This was actually a struggle in a lot of organizations. Some people were really forward and were talking about how great DevOps is working for us. Etsy is a good example of how they talked about how empowering this is for our developers to essentially just put code into production immediately. And don't you want to come and work for us, right? And have this rapid feedback and see your stuff in production. But there's also a lot of pushback, especially over change, right? Especially over people who have worked on this for a long time. And we see this not just with DevOps, but this will come up again when we talk about fairness, when we talk about security, safety, and we talked about hazard analysis in the past. Like, how do you get people to change their behavior? Organizational culture is this is how we do things in this organization. And different organizations have quite different organizational cultures. Are you aware of anything? Have you seen any contrasts by working for 2 different companies? Something that was just completely different between the 2? This is often in the air. This is not necessarily always written down, but this is how we handle problems. This is how we meet. This is how we make decisions. Any ideas? This is certainly exaggerating as a comic, but I think it has some truth to it based on what you hear from people who know those spaces. Like, Apple has a culture of not even telling their own employees what other teams are working on, right? Everybody's kind of secretive from everybody else. And I think that matters in how you share knowledge in an organization. If one team is successful with DevOps, will other people pick this up, right? Amazon has a very hierarchical top-down strategy. I think you can tell teams much more what to do. Microsoft had this notion of hiring a lot of people, telling them they're the best, and then they would never listen to anybody else. So they have a strong independence within teams, but not necessarily a great, they have a knowledge-sharing culture, but very hard of kind of convincing them. Move fast, break things. It's no longer their motto, but it's certainly deeply ingrained, right, in kind of acting irresponsibly in a way, whereas some companies are very much safety-focused and slower. Have you seen any of this somewhere? How did it feel different? What were kind of cultural differences?
Consulting, it was like meeting a lot in person, like a lot of hierarchy as well, whereas like the other team, there were like literally 2 people in my team, in my country, so it was like I can only speak to 2 other people.
Right, and make a lot of decisions locally, right, and a lot more autonomy. Oops, sorry. Yeah.
appear a little bit flatter because of layoffs.
Okay.
Yeah, the circles would get bigger because the words amount of work bigger.
All right. The point here is changing culture is really hard. Culture is something that's deeply ingrained in a company. Meta can say we no longer say move fast and break things, and we haven't said so in 10 years, but it's deeply ingrained in how a lot of people think there. It's ingrained in who they hire, right? So you have this self-repeating, self-reinforcing culture in a lot of organizations because they hire for people who behave in a similar way, or when you come there, you adjust because you want to fit into the team. Getting somebody to change that is really difficult, and a lot of organizations failed because they couldn't adapt. Culture is not just the things that are written down. That's actually, this is known as artifacts here, or espoused values, we say what we publicly say. Culture is usually the basic assumptions that we never write down, the ways that we're doing things here that you don't really see, that you observe over time. Culture change has been studied a lot, often comes with a lot of top-down focus. If management doesn't buy into things, like management doesn't realize DevOps is a good thing, or caring about fairness in our machine learning models is a good thing, caring about safety is a good thing, nobody will care in the company. You can try to do this bottom-up. You often have activists inside a company who care about safety, who are whistleblowers, or who care about fairness, who want to maybe improve deployment mechanisms and introduce DevOps, but it's hard to do against management. The best strategies to do this locally is often convince people locally in your neighborhood that this is a good idea. Often start small, show some small benefits on early steps, and then try to scale and convince management. This is something it's usually easier to start a new company to set a culture. It often comes with a founder. So don't expect that you can come into a company and just introduce MLOps or DevOps easily, right? You often have to do some work, either convince management or really do a lot of ground-up work, kind of find your community, do something. It's often really slow, really hard to change, and sometimes it might be better to just quit and work somewhere else if the culture is really not aligning with what you want to do. Right, so MLOps and DevOps culture is this thing it's a culture of working together rather than against each other in these roles and taking on additional responsibilities. As a developer, I do more stuff. I hopefully get some benefits of monitoring and releasing fast, right? But it requires me to do more stuff, to learn Docker, to learn these tools, and to be responsible if something goes down at 3 in the morning. So let me wrap up here. What I wanted to cover today is that DevOps is really important if you're planning for change, if you're thinking about experimenting, ever updating anything, or scaling in practice. Right? It's thinking about operations, service level agreements, like how much available, how fast, how scalable should the system be. And we have all these tools that are all about automation, about scripting things, about scaling things, about monitoring. I think they're really useful foundations to know about. You're seeing a lot of them in your team project. And MLOps is essentially the same thing, just with machine learning tools. All right, see you Wednesday.